Hello, everyone. Thank you so much for joining us today. This is Matthew. I'm on with Professor Impey. We have Alexander helping out with a lot of the technical stuff, and I'm going to hand this over to you, Chris, to get us started.
Okay, well, no delay. I'm sure there are a lot of questions and a lot of people online, so floor is open for your questions on astronomy.
Thank you very much, Chris. The very first question is from an email, and Martin would like to know, could dark matter or dark energy bend light so much that it could essentially take like multiple circuits of either a galaxy or the universe or a black hole before reaching us? So like taking like a 26 billion year detour. What's the furthest away light we've ever seen?
Okay, well, there's a few questions bundled in there, but I'll deal with the bending of light by dark matter or dark energy. For dark energy, it's a simple answer, which is that dark energy does not bend light. It's not, although it is an entity, a quantity of the vacuum of space that might be understandable in general relativity, there's no implication that it bends light. It's basically just something that causes the uniform expansion of space-time in 3 dimensions without regard to changing the trajectory of particles or light traveling through it. So no effect there. Dark matter, however, because it is mass and it has gravity, it does, of course, bend light according to general relativity. And in fact, the way we know there's 6 times more dark matter than normal matter is we look at big agglomerations of mass in the universe, like clusters of galaxies, and there most of the bending and most of the mass is from dark matter. So these gravitationally lensed situations that the Hubble Space Telescope and ground-based telescopes see are situations where most of the bending, by the proportion of dark matter to normal matter, is done by the dark matter. Now, could that curvature of the light trajectory caused by dark matter, could it actually cause the phenomenon asked in the question, like a complete circuit of light multiple times around the universe? No, because that would depend on the universe's overall mass density being high enough for the universe to be closed. So if there were more dark matter than there is, by a factor of 3 or so, then the universe would have been closed, geometrically closed by dark matter, which means that, yes, indeed, because of dark matter, light could travel around the universe, taking tens of billions of years for a circuit over and over again in essentially a trapped way in a closed space-time situation. But because there isn't enough dark matter to do that, we just see deviations of light traveling through the universe, not complete circuits of light. So as far as we know, there's no indication that light can make multiple paths or trajectories through our visible universe.
Thank you very much. The next question is from one of our live viewers, Ekjot. Can you explain the structure of the magnetic field of the sun?
Yes, it was quite a piece of research to understand the magnetic field of the sun. I mean, we'd guessed or intuited or inferred that stars and the sun in particular had a magnetic field hundreds of years ago. So the phenomenon of sunspots, which of course have been observed since the invention of the telescope for 400 years, that was imputed to be connected with magnetic fields. But the full unraveling of the sun's magnetic field and the understanding of the mechanism of sunspots and the sun's magnetic field reversal every 22 years didn't happen until the middle of the last century. So it needed theoretical insights from physics, but particularly the subject of magnetohydrodynamics, that is how plasmas threaded with magnetic fields behave, because that's what the sun is. It's a high temperature, high energy gas, diffuse gas called a plasma, and it's threaded by a magnetic field. And the other piece of theory that developed in the 1950s was the dynamo mechanism, and that's the mechanism by which a small seed magnetic field can grow over time, and that magnetic field, which operates in a simple way like a dipole, just like the Earth's magnetic field is the dipole, like a bar magnet almost. In the sun, that field is more complicated because the sun rotates differentially. It rotates faster at the equator than the poles. And so the magnetic field lines that are trapped within the solar plasma will gradually get wound up by just the regular rotation of the sun at the point at which they get sufficiently wound up, the magnetic field essentially reconnects and dissipates and has to reform again. So this mechanism of the growth of the magnetic field and its eventual tangling and dissipation on a regular cycle, it took a while to figure out. A man called Eugene Parker, who spent most of his career at the University of Chicago, a very famous physicist and theorist, he developed the solar dynamo mechanism and became famous for it. And in fact, the most recent and best NASA probe of the sun is now called the Parker probe after Eugene Parker.
Excellent. Thank you very much. The next question is from Jose, who is on with us live. How can you measure the diameter or radius of a star, and what's the best way to get an accurate value?
So it turns out that the size of a star, diameter or radius, is often an indirect measurement. It's often inferred from a model. So the number of stars that have actual direct size measurements is actually very small. It's hundreds, but it's a small fraction of the number of stars, even visible to the naked eye in the night sky. And so we can only measure with telescopes above the Earth's orbit. We only have sufficient angular resolution to see the size of a star in the sky, for stars that are either very nearby or intrinsically large, like giants and supergiants. And so those are the stars for which we've directly measured a size with astronomical measurement. For the vast majority of all stars, really 99.999% of them, almost all of them, the size of a star is an inference. What we typically measure for a star is its luminosity. If we know its distance, we can say how much luminosity or photons per second it's putting out in all directions. And if we understand where it gets its energy from, typically by fusion of hydrogen to helium for a main sequence star, then we can make a model of the star. And that model, where we know what the energy source is and we know what the distance is and the amount of luminosity coming out, will lead to an inferred size. It's just a stable configuration which creates enough pressure and temperature in the core to produce the radiation we see. So for most stars, the size is actually a calculated number. It's not an actually observed number.
Excellent. The next question is from an email. Gabriel would like to know which is the minimum size for an asteroid so that it represents a threat for life on Earth in a hypothetical impact?
Right. So that's an interesting question. And of course, it partly depends on speed. It's not simply the size, it's velocity, because the energy deposited when an asteroid or comet or meteor impacts the Earth goes as the kinetic energy, and that's half the mass times the velocity squared. So the energy deposited on the Earth is much more sensitive to speed than it is to mass or size. But that bearing in mind, the typical relative velocity of an impactor on the Earth is tens of thousands of kilometers per hour, so maybe 50 to 100,000 kilometers per hour, very fast. So that's one variable. Now the mass, for those typical speeds, what mass will cause a mass extinction, or possibly the worst case scenario, a sterilizing impact on the Earth? And that boundary typically is around half a kilometer. Anything about over a few hundred meters traveling at that typical speed will, regardless of where it hits the Earth, will produce such a dramatic deposition of energy, global tsunamis, deposition of particulates in the atmosphere that lead to nuclear winter or a vast change in temperature which destroys the food web, plus all the direct impact catastrophe on life. So somewhere around half a kilometer or higher, definitely it's going to be a mass extinction and possibly a sterilizing impact. The level at which we don't have to worry, well, if you want to take an example, we think that the Tunguska impactor, comet or asteroid, it's not quite clear what a fragment of what object that was estimated to be between 20 and 30 meters. And that obviously, it exploded in the low Earth atmosphere above Siberia, and it flattened thousands of square kilometers of forest and killed most of the animals nearby. Luckily, there were a few people nearby. Maybe some were killed, but not many. So at the level of a few tens of meters, you've got a regional devastation if it happened to hit a city, but most of the world would survive. So the boundary at which you really start caring about these things is probably around 50 to 100 meters.
It's good to know. And then I guess kind of a follow-up to that question is, could we, like, what's the smallest or what's the largest size of an asteroid that we could potentially do something about, or, affect its trajectory?
Right. So in terms of protection, planetary protection, NASA was actually mandated by Congress a decade or so ago to put in place programs that would find all objects smaller than about 250 meters in size. And so it was going to find everything bigger than 250 meters, and those are definitely a devastation on the level of a large country. And so it took a long time. NASA's pretty much completed that job with a network of telescopes looking for near-Earth moving objects. So we've cataloged pretty much everything that's above about 250, maybe down to 200 meters. Objects smaller than that can still cause a big problem when we have measured many of them, but we don't have a full catalog of them. So the first part of mitigation is, of course, knowing what's out there. And so the slightly uncomfortable answer is we know everything that's out there above 250 meters, which would be a huge problem for the Earth, but we don't know all the things that are about 100 meters or 150 meters, and those would be regionally devastating. So there's more work to do. In terms of the second stage, once you know that such an object exists and it's potentially on an Earth-crossing orbit, their progress has been excellent because of the computers. Well, two things: because of the telescope networks that track the orbits of such objects. So as soon as one is identified and its size and distance are known, then telescope networks get together to plot its trajectory or orbit with better and better precision. Then we throw computers at the situation to understand or predict the probability that it could impact the Earth. And those telescope networks and the power of those computers has improved a lot in the last decade. So it's fairly reliable now to go from identifying a potential impactor to calculating and estimating the probability that it would hit the Earth. And when that's done, the probability is almost always a low number because space is big, impactors are small, and the odds of a collision are just very, very low in general. But say that probability was not low. Now you're at the third stage, which is doing something about it. And those mechanisms also exist. We've already landed spacecraft on small objects, on comets. In several cases, we've had that happen just within the last year from a Japanese probe. So we have the technology to rendezvous with a fast-moving interplanetary object and land a rocket on it. Because we have that technology, we also have the capability of landing on an object like that, tethering the spacecraft, and using thrusters or rockets pointing upwards to deflect it in its trajectory. So we have a mechanism to rendezvous with the potential impactor and steer it away from hitting the Earth. We've demonstrated all aspects of that technology. And all that's really required is enough lead time so that it's not a desperate scramble to save the Earth. And luckily, the telescopes that find these things tend to find them when they're hundreds of millions of miles away and typically years away from approaching the Earth. So should one emerge that seems to have a significant probability of hitting the Earth, and that calculation relentlessly shows that probability rising as it gets closer, then we do have a mechanism to do something about it.
Thank you very much, Chris. And just a quick message to all of those who are with us live. If we don't get to your specific question, we have dozens, I think now it's around 60 or 70 previous live sessions where we have answered hundreds of questions. So you definitely should check out those previous live sessions if we don't get to yours, because there are questions that come up periodically that are similar or the same as questions that we've asked and answered before. And so we do our best to get to all of your questions. That being said, here's one that comes up fairly frequently. Can you talk about what is dark matter and what is dark energy?
So dark matter and dark energy are the two most ubiquitous ingredients in the universe. They account for most of the mass energy of the universe. The normal matter, the protons, neutrons, and electrons that we're made of and normal stars are made of, represent about 4% of the universe. Dark matter is about 26%, and dark energy is the rest, about 70%. Dark matter, we think, is a fundamental subatomic particle that is an extension of standard physics. We think that because we've ruled out all larger things. We know dark matter can't be black holes, dead stars, things too small to become stars, rocks in space, tiny dust particles. A lot of ruling out has been done in the last few decades. So we think it's a fundamental subatomic particle, and luckily, within extensions to standard physics, there are some plausible candidates for the dark matter particle. The requirement is that it not interact with light or emit or absorb radiation. So physicists are on the hunt for such particles, with typically experiments done in deep mines to shield from cosmic rays, looking for the dark matter particle to interact with a solid state detector. That's the hunt for dark matter, and there's some optimism that that hunt for direct detection of dark matter, which we know exists in the universe from astronomy measurements, will succeed within maybe 3 to 5 years. Dark energy, the scenario is really quite different. Dark energy is the ubiquitous dominant ingredient of the universe, causing accelerated expansion, an observation made from the 1990s and then confirmed multiple times since then. But we have no theoretical basis for understanding dark energy in terms of standard physics. So while dark matter might be a modest and perhaps not surprising extension of standard physics, dark energy represents a radical extension of standard physics. It's really an ingredient in physics that we don't understand at all. So that's one problem with dark energy. The other problem is there are very few observational handles on it, apart from measuring accelerated expansion and demonstrating more recently that dark energy doesn't seem to vary with time and across space and through cosmic time. We really don't know anything else about it. And so our agenda of trying to understand dark energy is pretty much stalled at the moment, and we're making very slow progress.
Excellent. Thank you very much. The next question is from Saqib, who's on with us live. When observing Doppler shift from starlight, how can we be sure that an exoplanet is causing the shift? Why not consider that the star might be part of a binary star system, or could this shift be caused by something else?
Yeah, that's a good question. And early on in the discovery phase of exoplanets, people worried a lot about that. I mean, the bar was set very high on proving that these periodic Doppler shifts in stellar spectra of a seemingly isolated star were actually caused by planets and not by some other effect. And it actually took a few years, maybe even 5 or 6 years, for astronomers to be very confident and comfortable that they were looking at planets and nothing else. So how do they show that? Well, first of all, they make very deep imaging observations, and they are typically planets around relatively nearby stars, a few hundred light years away. And so for most type of binary systems that are wide systems, it would be easy to see the stellar companion, even if it was a faint star like a white dwarf. So ruling out binary stars is actually quite an easy thing to do. Also, the amount of the Doppler shift itself tells you that the object you're looking at is actually too small to be a star. The biggest exoplanets are about 5 or 8 times Jupiter's mass. And then there's a sort of hole, if you like, in the mass distribution where we don't see more massive planets. And so it's very clear that the most massive objects causing Doppler shifts in stars are the size of gas giant planets or somewhat bigger. They're not big enough to be stars, so we can rule out binary systems. Now, something that gets harder, however, is what if the Doppler shift is caused by some internal effect within a single star, the star itself? And that actually is the reason why the Doppler method for exoplanet detection is running out of steam in its sensitivity around about an Earth mass. So if you work out what the Doppler shift caused on a sun-like star by an Earth mass planet is, it's actually low enough that that's very similar to the velocity of normal atmospheric motions in a star itself. And so you could get confused by looking for an Earth-like planet with the Doppler method between the normal turbulent motions of plasma and the outer layers of a star. It acts essentially like a noise floor that limits you detecting much less than an Earth mass planet with the Doppler method. And so that has, in fact, been a practical limitation. There are clever methods to try and beat down that noise or average it out that might let you go a little bit below Earth mass, but the Doppler method seems to be finishing its sensitivity there. The transit method, of course, is sensitive to smaller objects, and we've already found Mars mass planets with that method.
All right, thank you very much. The next question is from Anne, who's on with us live. Will the Gaia satellite make spectroscopic parallax obsolete in a few years, since we will have accurate distance measurements to millions of stars?
It's a good question, and the simple answer is yes. The Gaia satellite is rewriting the book on stellar astrometry and rewriting, giving us an encyclopedia of stellar positions. And it has such sensitivity, and it's looking at so many stars that it does indeed sort of make the normal ground-based spectroscopic methods a little bit obsolete. So spectroscopic methods are now being used for things that Gaia can't do. So for instance, there are types of binary stars called spectroscopic binaries, where the binaries are far enough away and so close to each other that even Gaia can't separate them out or resolve them. And there we actually map out their orbits with spectroscopic techniques and Earth-based telescopes. So there are a few subclasses of stars and binary systems where we do need spectroscopic methods from the Earth. But yes, for the bulk of the sun's neighborhood of the Milky Way, Gaia is going to give us all the data we need.
Okay, the next question is from Isaiah, who's on with us live. There are blue stars and red stars and yellow stars and white stars. Is there such a thing as a purple star? And if not, why not?
Well, in terms of spectral properties, if we just take the optical spectrum, red, orange, yellow, blue, green, blue, indigo, violet, if you're talking about a purple star, you'd be talking about something that has a very short wavelength of effective radiation. So most of its radiation is coming out at very short wavelengths at the blue end of the spectrum, or perhaps even beyond in the ultraviolet. And so you can ask the question is what is the temperature of a black body where the peak radiation would correspond to something that we would call purple, the color purple or violet or indigo even. And yes, you can work out that temperature, and those stars do exist. So it's a reasonable question, and it has a simple physical answer. And the simple physical answer is these would be stars of about 30 to 40,000 Kelvin. So around the temperature of some white dwarfs, and that they would have the bulk of their temperature coming out literally as violet light. They'd also emit ultraviolet light, like beyond what the eye could detect. And blackbody radiation actually is quite broad. It spans an order of magnitude in wavelength or more. So stars never have one single color. They always have a broad range of wavelengths.
Thank you. The next question is from an email from Christina. How did water appear on Earth? Is Thea's impact hypothesis still our best bet?
So this has been a fairly controversial field. It's not my field, but there are planetary scientists who work across the street, and I talk to them fairly regularly about this. It's been controversial because, the Earth's oceans are obviously critical to life on Earth. And so where the Earth got its water is related to the question of where do terrestrial planets like the Earth get their water, and therefore what's the probability that they might host life. So it's a very important question for astrobiology. And it's been difficult to answer for a couple of reasons. First of all, the Earth got its water very early on in its history, and the main argument for quite a while was whether the water that exists now on the Earth in its oceans, which is a very small percentage of the Earth's mass, less than 1/100% of the Earth's mass. We think Earth is a watery planet, but really it's mostly a rocky planet. Was that water there initially at the formation, or was it added afterwards? And the Thea idea and other impact ideas, or is called the late veneer theory, the idea that the water was added by a set of impacts of water-rich or icy material from the outer solar system being deposited onto the Earth in the early days when the solar system was still full of debris left over from the formation of the planets. And that was the favorite explanation for a while. but the momentum or the tilt has changed to another idea, which is that the water was always there. And that's because we've got new data on the water content of the Earth's mantle. So the Earth's mantle is inaccessible to us by direct digging. So we have to use indirect measurements to understand the sort of either the hydrous mineral content of the water, that is, minerals that have incorporated water at some time in their past, or the actual presence of water in deep rock space. And as that research has moved forward, it's become clear that there is probably indeed enough water in the early Earth as it formed to eventually percolate up and cool and form the Earth's oceans. You don't need to deposit it from outside. So in a sense, that has now become the favorite theory.
Okay, the next question is from Dave Gamesters, who's on with us live. We've talked a lot about neutrinos and various answers. What are neutrinos?
Neutrinos are fundamental subatomic particles. The word comes from the Italian for little one, because Enrico Fermi, a famous Italian-American physicist, he gave them their names. And they were first, they were inferred in a particle reaction and a decay where there appeared to be a missing amount of momentum and potentially mass. And so it was attributed to a small, essentially invisible particle that had left the situation. Neutrinos were predicted out of these particle interactions, and they weren't actually detected in the lab for another almost 20 years, I think. Anderson was the name of the physicist who first detected neutrinos, got a Nobel Prize for that. So neutrinos are fundamental subatomic particles. They're very light, but we think they're not massless, because in the last decade or so, we've observed that the three different flavors of neutrinos oscillate or can change from one to the other. And that essentially would not be possible unless the neutrinos actually had some small level of mass. So they have mass, but it's a small amount of mass, not actually determined yet. And it's not sufficient for them, for example, to be dominant cosmologically. So we know that neutrinos couldn't close the universe or form a significant mass component of the universe. In the realm of particle physics, there are families of particles. And as there are three families of particles, there are three types of neutrinos. There's the normal neutrino, which we call the electron neutrino. There's the muon neutrino, which is twinned with the muon particle, which is an intermediate mass particle. And then there's the tau neutrino, which is twinned with the tau particle, which is a massive particle, subatomic particle. And so neutrinos twin the schema in particle physics of three different families of particles. Now, why did neutrinos exist at all? Why are there three families? These are things we actually don't know. We need more profound theories of matter to really understand neutrinos. What mass do neutrinos have? That's a matter for observation, experiment, and we haven't yet managed to pin down the mass of any one of the flavors of neutrinos, because all we can see is oscillations between the three states, not the individual mass of one neutrino in one of those states. But neutrinos, to sum up, are important fundamental particles because they're as abundant in the universe as electrons, protons, and neutrons. So there are an enormous number of neutrinos in the universe, about 1 with 80 zeros after it.
Thank you very much. Astrogate, who's on with us live, would like to know, do we really trust our stellar but really cosmological models enough to be sure that dark matter, or for that matter, dark energy, is not the result of some fault in these models?
There's always a concern about that, and scientists, if they're doing their job correctly, should never assume that they've figured out something, and they should keep their options open, especially when we don't have a deep physical understanding, especially of dark energy. So for dark energy, it's definitely the case that the people are keeping an open mind. For dark energy not to exist, for it not to be a thing we need to worry about, then the observations of the accelerating expansion would have to be wrong. Now, those observations, since they were first done 25 years ago, have been redone and tested many times over. And that observation is fairly robust. So the universe is accelerating, and it's an expansion, and we impute that to something we call dark energy. So given that that observation is robust, then inferring something with the properties of dark energy seems reliable. But remember, we don't know what it is at all. Is it possible that physics is fundamentally wrong in some more profound sense, and so we don't need dark energy? Absolutely, because we don't have a final theory of physics yet. And for dark matter, it's essentially the same story. We have a lot of astronomical observations that lead us to believe that something that we call dark matter exists, which is to say mass that dominates normal atoms, protons, electrons, and neutrons by a factor of 6, and is more widely distributed than them cosmologically. So it's a dominant ingredient of the universe. We have reason to believe it exists because of the lensing of light and many other reasons. But these observations don't tell us what dark matter is. The escape clause for dark matter traditionally has been, what if Newton's theory is wrong? Because our inference of dark matter really depends on Newton's law of gravity applying on large scales and relatively weak amounts of gravity where you don't need Einstein's theory. So if Newton's theory was wrong on large scales for some reason, or had to be modified, and there's a theory called modified Newtonian dynamics, MOND, which every now and then gets attention, and it's mostly been refuted, but not entirely, as an alternate theory. So it's a complicated and somewhat confusing landscape where we can't absolutely rule out a profound physics issue that is leading us astray in the fact that we believe dark matter and dark energy exist.
Thank you very much. The next question is from, Harshul, who's on with us live. Who'd like to know, why doesn't our galaxy, the Milky Way, have a quasar?
Good question, and some people have speculated that our galaxy might have had a quasar in the past. The main reason it doesn't have a quasar is because the mass of our black hole is actually pretty puny. So the black hole masses scale with the old star population of a galaxy, and our galaxy is a modest spiral galaxy which doesn't have a huge number of old stars. So in general, the most powerful quasars and radio sources in the universe are in elliptical galaxies, more massive galaxies than ours, which have a large number of old stars. So given the correlation between black hole mass and galaxy mass, even then our black hole is quite small, 4 million solar masses. So the first reason it's not a quasar is just it's not really big enough to be a quasar. Even if it was accreting matter, it wouldn't be luminous enough to meet the quasar designation. The other reason it's not a quasar is it's not in an active phase as we speak. So it appears that in a previous episode of activity, the central black hole in our galaxy had emitted enough radiation and plasma to evacuate a hole in the center of our galaxy. So there seems to be a little bubble, a low density bubble near the center of our galaxy, which is an indication of a previous episode of activity. And people trying to do archaeology of this, sort of cosmic archaeology, have made the intriguing suggestion that perhaps 5 or 10 million years ago, our galaxy was active. Maybe not active enough to be called a quasar. Maybe we'd have called it a Seyfert galaxy or something like that. And that's very provocative. So mostly our galaxy is not a quasar because it's too puny a black hole, and also it's inactive. But were it to go into an active phase, it would be a pretty spectacular object at the center of our galaxy.
Excellent. The next question is from Jason, who's on with us live. Can you explain the formation of the aurora borealis on Earth, and then also, any aurora around the solar system?
Sure. So the aurora borealis and its analog, the aurora australis in the southern hemisphere, are both associated with the interaction of high energy particles and radiation from the sun with the Earth's magnetic field. So, and the reason these phenomena are concentrated near the poles of the Earth is because that's where the solar wind, so the solar wind is an outflow of high energy, very diffuse, very low density, high energy plasma and high energy particles called cosmic rays from the sun. When that radiation reaches the sun after traveling 150 million kilometers, it interacts with the Earth's magnetic field. In the situations where the Earth's magnetic field is going into the Earth, because it's the poles of the dipole magnetic field, then that radiation can funnel much more tightly and converge. And so that radiation, which consists largely of charged particles like protons, interacts with the ionosphere, the magnetically threaded ionosphere, and accelerates those particles. It's a standard mechanism. Synchrotron radiation, for example, is one mode of this radiation. So in the lab, we actually accelerate particles with magnetic fields and they radiate. The shimmering, amazing, so the colors are not directly caused by that radiation, but they're caused by fluorescence. So the energy deposition from high energy particles and radiation from the sun into the upper atmosphere causes the gas particles of which the atmosphere is made to fluoresce. And that's the oxygen, that's the ozone, that's the nitrogen, and other trace gases. And that fluorescing creates characteristic lines. Oxygen has characteristic line, for instance, in the green part of the spectrum. So you see green tinged aurora that are actually directly caused by the oxygen component of the atmosphere. Ozone and nitrogen have other different wavelengths of their fluorescing. And so the colors of the aurora are caused by fluorescence of the atoms in our Earth's atmosphere that have been energized essentially by this inrushing radiation. The concentration near the poles is caused by the convergence zone of the Earth's magnetic field near the poles, and the fact that it happens closer to the surface there. And the changing nature of it is, of course, because the Earth's atmosphere is a dynamic thing. There's turbulent motions and convection, and so the Earth's atmosphere is not static. And so the amazing ripples and sheets and curtains and striations and incredible phenomena that you can see in a video of the aurora are caused by the activity of the Earth's atmosphere, just made visible by these particle radiation interactions.
Naroon Joe, who is on with us live, would like to know, is it possible to use energy to manipulate gravity or space-time? I'm not sure if he means, does energy manipulate, or could humans use energy? So perhaps you could address both of those questions.
Right. So I'll answer them as two different questions. Can we use energy? Does energy affect space-time? And the answer is yes. The curvature of space-time, or the effects of space-time that are inferred and calculated using general relativity, are caused by mass and energy, mass and or energy. And so mass and energy are related by E equals mc squared. And in general relativity, what Einstein was saying was that mass energy curves space-time, two hyphenated quantities related to each other. And so yes, pure energy can cause the curvature of space-time just as well as mass can. And if you want to work out how much equivalent mass it would be, you just use E equals mc squared. And we've seen examples of this effect. And so that's an important answer. Now, the other question, which is more of a technology question, is could we use energy, our control of energy, our creation of energy, to alter space-time itself? That is something that's beyond our capability. So our ability to control and create sufficiently large amounts of energy to bend space-time is extremely limited. We can create phenomenal amounts of energy in explosive and dangerous situations like a nuclear bomb, but otherwise the amounts of energy we can control and harness are truly modest, and they're just not sufficient if you work out general relativity to cause any noticeable effect on space-time.
Right. The next two questions are kind of related. I can't find the person who asked the first one, but the first question is, why did all the planets in our solar system end up orbiting kind of on the same plane? And then also, but then why is Earth tilted on its axis at 23.5 degrees?
Mm-hmm. So why did all the planets orbit in the same plane? That's really down to the formation scenario of the solar system. So we believe, with fair confidence, because we've simulated it and we see sort of indirect pieces of evidence of the history, we believe that the solar system started as a large nebulous gas and dust cloud, much larger than the current solar system, and that it had some small amount of rotation, because most gas clouds in the universe, just through turbulent effects, do have some rotation. And because of that rotation, it was more inclined when it suffered a trigger to its collapse. And there's some indication that the solar system collapsed, or the cloud that would form the solar system collapsed because of the detonation of a nearby supernova. So that impulse would be sufficient to trigger collapse of a cloud. That collapse would happen preferentially along the polar axis of the rotation because it's not resisted by angular momentum in that direction. And so that's how you turn a large, mildly rotating, almost spherical gas cloud into a much smaller, much more rapidly rotating disk of gas and dust. And from within that disk of gas and dust, the densities are high enough for planets to form slowly by accretion. And that process took about 50 million years early in the solar system. So that's why all the planets orbit the same way around the sun, and why all but Venus, at least, spin the same way that they orbit around the sun. Now, it's the question of why the Earth has a spin axis that's tilted by 23.5 degrees from its orbit of the sun. That's a very interesting question, because if we look at the rest of the planets in the solar system, we see that the gas giants, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, have spins that are almost perfectly aligned north-south. They just tilt by a few degrees from true north-south or true equatorial plane. It's only the smaller planets that show a different tilt. So Venus is tilted by 180 degrees because it's spinning the wrong way. It's counter-rotating. Mars and the Earth share a similar. Mercury has a very small orbital tilt, probably because it's locked tidally to the sun. And so the Earth and Mars, the other 2 terrestrial planets, have tilts that are actually quite similar. Mars about 25 degrees, Earth 23.5 degrees. And these tilts can arise naturally just by interactions, just by the fact that these planets are not tidally locked to the sun, so there's no arm of gravity reaching out and gripping them so tightly that their poles can't wander. And they're subject to interactions over billions of years and billions of orbits of the sun, of course. And so these perturbations or influences from external objects and gravity over a long period of time can influence the pole and cause the pole axis to wander. And that indeed has happened. We know, for example, that the Mars tilt has varied between 25 degrees, maybe it's gone as little as 20, and as much as 50 degrees over cosmic history. The Earth's tilt is more interesting because of that. It's a significant tilt. We don't believe the Earth's tilt has wandered, and that's because of the effect of the moon. So the moon is a large moon relative to the planet, the biggest moon relative to planet size anywhere in the solar system. And so given that the Earth acquired a skewed tilt probably early on in its history, the moon has since stabilized that tilt. And so that stabilization means that over long periods of time and the evolution of life, the Earth's climate has been relatively stable. The seasonal variation really hasn't changed from one epoch to another, which may have been important in the development of life. We don't know.
Excellent. The next question is from Manikandan, who's on with us. Oh, so I'm sorry, that was the last question. From Anan, who would like to know what are asteroids made out of, and what are the different types of asteroids, and what makes them different?
There's a whole typology of asteroids with different letters attached to them, and I'm not expert enough on this field. It's way outside my research field to give you all the different names of the different types of asteroids, but they basically refer to the type of rocky material they're made of. Most asteroids are made of mixtures of rock and ice, and they're predominantly rock rather than ice. Comets are more equal proportions of ice and rock. And the different types of asteroids essentially reflect their formation scenario. So asteroids that formed in the asteroid belt spans quite a large range of distances from the sun. It's not actually one narrow little band, it's quite large. And so in the formation scenario of the solar system, the type of rocky material, the density, and the types of minerals that form the solid objects varies significantly from the inner edge of the asteroid belt to the outer edge of the asteroid belt. And so there are compositional differences between asteroids depending on their distance from the sun. So some have larger fractions of metals compared to rocks, some have larger fraction of rocks, and they have varying fractions of frozen gases, or volatiles as they're called. It's a very rich field, and there's some patterns in these properties that are understood, and there's some patterns that actually are not understood. There's still open research questions about the composition of asteroids.
Excellent. The next question is from Mr. Fanditube, who's on with us live. Is SpaceX's actually, there was just news recently that they were pausing launching some of these SpaceX satellites. And with that in mind, is SpaceX Starlink's mega constellation going to cause any problems for astronomy, or has it already?
It has already, and in its full projection of tens of thousands of satellites, it will cause significant problems for deep astronomy using facilities like the Large Synoptic Survey Telescope, which take Hubble depth picture of the entire sky every few days. These telescopes are so sensitive, they will see the SpaceX constellation of satellites, in particular when they are near the horizon, so near sunset and sunrise, and they're quite bright streaks across the sky that will interfere with deep imaging. SpaceX is aware of the situation. I went to a special session and gave a talk at a special session at the American Astronomical Society meeting in Honolulu in January, where SpaceX had a senior representative, it wasn't Elon Musk, to talk about the fact that the company is aware of astronomers' concerns, is not ignoring it. Of course, SpaceX is driven by the bottom line. It's a commercial company. They're not there to make astronomers happy. However, they have already changed the coding, the type of coding they put on these satellites to try and minimize, with some matte black surface, the reflectance of the satellites. The signs so far are, in the first set of satellites released with the new, or launched with the new coding, that it mitigates some of the problems, but not really a lot in the event that there are tens of thousands of them. So I'd say it's not quite a standoff, but it's a continuing issue for astronomers, because the SpaceX constellation, when fully deployed, will absolutely compromise some of the deep surveys astronomers are planning.
All right, we have a couple of astrobiology questions coming up. The first one is, have we found any evidence for life on Mars, for example, microbes or things like that?
No, there was, as you probably know, if you have a long memory, there was a famous press conference where this was under President Bill Clinton, where the NASA administrator and Bill Clinton and other senior scientists got there on a stage and said that microbial life on Mars had been detected in the Allen Hills meteorite, ALH 84001. So that rock became very famous for not just that day, but for years, because it was a Martian meteorite where it seemed that there had been traces of microbial life, sort of evidence of past microbial life in many microfossils and chemical imbalances in the rock and magnetic minerals that seem to only be associated with life on Earth when you find them with microbes here. Almost all of that, I'm very carefully saying almost all of that evidence has dissipated over time. So the evidence on the Allen Hills meteorite has gone from, wow, that looks really good, evidence that there was life on Mars once, to inconclusive, to not proven at all. And so most scientists are not convinced. Similarly, there's been no other evidence claimed since then of life in any, or examples of fossilized life in any of the roughly 100 Martian meteorites we've found. And that's sometimes that's partly bad luck, because almost all the Martian meteorites that we've recovered are igneous rocks that have undergone extremely complex, hot, dense histories in magma. And so you would expect fossilized life traces to be destroyed by that history. Just by dumb bad luck, we haven't had sedimentary Martian meteorites to study where the fossilized microbes could have been preserved. So then we're left with what we find when we go to Mars, and none of the rovers so far, the Mars 2020 rover now scheduled to get there on 2022, will actually be the first rover with possibility to detect life. So I would say, as we speak, there's no evidence for present or previous life on Mars, but in part it's because our experiments have not been very convincing, or there's a very difficult experiment to do. And I'll even remind people that we had two space probes in the mid-1970s, the twin Voyager spacecraft that landed on Mars, first man-made objects to Mars, and they each had life detection experiments in them, and one of them, apparently, even to this day, is claimed by person who built it to have led to an inconclusive result that could have indicated life on Mars with a metabolism that wasn't based on photosynthesis. That's controversial. So it just shows that it's a very difficult thing to prove. So basically, we need a new generation of life detection experiments to look inside the rocks on Mars, and even better, to bring samples back to the Earth.
Thank you. The next question is from Sori, who would like to know, when searching for life on exoplanets, or planets in our own solar system, are the scientists looking for something that is exactly like life on Earth, or are they somehow looking for other possibilities of ingredients that could support other kinds of life, and how could they do that?
Yeah, that's a very important question, because if you only look for the thing you know, that's the only thing you could possibly find, and you've made yourself blind to other forms of life that are not quite the way our life works. So that's a really important issue to understand. So on the other hand, it is easier to look for the thing you know. So it is the case that for some of the future planned Martian experiments, we will be looking for nucleic acids. We will be using something like PCR, polymerase chain reaction, which is a way of taking small amounts of genetic material and amplifying it, RNA and DNA. So in these instances, we will be using technology, as we do on Earth, to manipulate our form of genetic material and detect it. And so that's making a pretty strong assumption about what life on a planet is like. Now, we can't do those experiments on exoplanets. These are just experiments I'm talking about for Mars, and possibly at some stage for Titan and Europa. On exoplanets, it's even more crude. On exoplanets, we're looking at the alteration of their atmosphere by microbial activity. And the one that makes the most obvious tracer is, of course, the metabolism where the respiration leads to the intake of carbon dioxide and the extake of oxygen, which has led to the oxygen in our atmosphere. So if we look for analogies of the microbes that oxygenated our atmosphere, then we can do that experiments on other planets. However, there was a time in the Earth's history early on when we did not have oxygenic photosynthesis, when the microbes were methanogens. Their metabolism was based on methane, and methane was released as a byproduct, as it is from some forms of life now. And so their methane would be the biomarker and the tracer you'd look for. So for exoplanet research, they're looking for methane, they're looking for oxygen and ozone, water vapor, of course, because you need water for life. And these are more broad spectrum in the sense that there's a range of microbes on Earth that do oxygenic photosynthesis, or photosynthesis in general, and there are a range of microbes on Earth that emit methane as a byproduct of their metabolism, but that's not the only possible metabolisms or the only possible life forms. So to summarize, we are mostly looking for what we know, or what we have experience of on the Earth, if not now, in our history. And that's a broad sweep, but it's not all-encompassing. And so if life were really strange and had a basis that was not based on, well, for instance, carbon chemistry or cells or nucleic acids, then we'd be in trouble. We wouldn't be able to detect it.
All right, we have time for just a couple more questions. The next question is from Crispy, who's on with us live. Does the moon have a magnetic field? And if so, how would a lunar magnetic field affect us individually on Earth?
The moon has, if not completely absent, extremely weak magnetic field. So essentially it has no magnetic field. And for its size, that is unusual, because there are objects close to the moon's size elsewhere in the solar system that have magnetic fields. We think the fact that it has no magnetic field is a consequence of the way the moon was created. The moon was created by an impact of a Mars-sized object on the Earth when it was very, very young and still molten. And the moon essentially splashed off crust and mantle rock was splashed off Earth, crust, and mantle rock into space that aggregated into the moon-sized body. And because that splashed off material did not penetrate down to the metallic core of the Earth, the moon does not seem to have a metallic core, and the metallic core is, of course, what tethers the magnetic field. So that's the fundamental reason why the moon does not have a magnetic field. It's associated with the way that it was formed. And there's an interesting NASA exercise that I've done with students over the years where you're hypothesized, it's a team building exercise actually, you're hypothesized to have landed on the moon, crash landed on the moon, but survived, and you have a bunch of stuff, and you can get to a place where you can be rescued if you can travel across a few hundred kilometers of the moon's surface. And you have all these things that crashed out of the spaceship that you have available to you, and you have to decide what to bring, what's important to your survival and what's not. And there are many objects, you know, rope and obvious things like that. One of the objects is always a compass. And that's sort of a trick question in this team building exercise, because the moon doesn't have a magnetic field, so navigating on the moon with a compass won't work. So that's how NASA has put that into one of their astronaut training exercises.
All right, and the final question for the session today is kind of a combination of a couple questions, but Sasi asked the original one. What are the alternatives to optical astronomy for research we are exploring, and what are the limitations of optical astronomy, and how do these alternatives overcome the limitations to optical astronomy?
Optical astronomy is the father of all astronomy, of course, because we have eyes and we've been doing naked eye astronomy for tens of thousands of years, and we've had telescopes for over 400 years, and they just get bigger and bigger. So optical astronomy is still the central astronomical science, because we have exquisite and large telescopes that work at optical wavelengths, and a lot of the interesting phenomena in the universe occur at visible wavelengths, like most of the transitions in energy state in atoms happen at visible wavelengths. So spectroscopy is very powerful at visible wavelengths. But that doesn't mean optical astronomy is everything. And so radio astronomy was the second different wavelengths region to be opened up in the 1940s and 50s. And radio astronomy is extremely good at looking at the high energy phenomena in galaxies and also low energy phenomena, because radio waves are low energy waves elsewhere in the universe. And high energy radiation is X-rays, and X-ray astronomy has been around since the 1960s, and that's extremely valuable for looking at compact objects, the environments of black holes, very hot spaces like the supernova remnants or the regions around dying stars. And so each of these different types of astronomy has its own niche, and it's a big niche. I mean, radio astronomy does not just look at one thing, it looks at galaxies, stars, not so much stars, but nebulae, interstellar medium, and so on. And X-ray astronomy looks at many things too. Looks at clusters, looks at galaxies, looks at black holes, looks at stellar corona. So astronomy is multifaceted. And while optical astronomy, I would say, still dominates, if you want to say what fraction of all the research papers that are published every year are optical astronomy versus the other wavelengths, I would say it's an interesting question. I'd have to look it up, but I'm pretty sure that the majority of all astronomy papers are still optical astronomy. But these other niches of astronomy are important, and actually we will never learn all we want to know about the universe without taking a panchromatic approach where we gather radiation all the way from radio waves to gamma rays to learn about what's going on out there. So thanks very much for all your questions. Great questions today, as always. We'll be back with you next week.